Welcome everyone. So today we'll learn about lande factor, and we'll learn about what is lande factor, how to calculate it, and we're going to discuss some problems also. So lande factor. Lande factor is a dimensionless quantity that characterizes the magnetic moment and angular momentum of an electron, particle or nucleus, specifically for an electron with both spin and orbital angular momenta. The magnetic moment of the electron in an atom arises due to its orbital motion around the nucleus and also due to its spin. The orbital magnetic moment mu L is equals to minus E by 2m into L, and that due to spin mu S is equals to minus 2 into E by 2m into S. Now the total magnetic moment of electron mu Ls is equals to mu L plus mu S, which is equals to minus E by 2m into L plus 2s. This mu Ls is the total magnetic moment of the electron. The total magnetic moment of electron mu Ls is equals to mu L plus mu S, which is equals to minus E by 2m into L plus 2s. Now we define total angular momentum vector J in terms of L and S. So J equals to L plus S and mu Ls equals to minus E by 2m into J plus S. Now from this diagram we can understand it very clearly. As we know, the total angular momentum J is equals to L plus S. So here you can see that J is the resultant of L and S. Now mu L will be directed in this direction and mu S will be directed in this direction, where mu L and mu S are the magnetic moment due to the orbital motion of electron and due to the spin of the electron. Now mu Ls is the sum of mu L and mu S. So this will be the sum of mu L and mu S, that is mu Ls. But as we know that L and S will precess around J, this L vector and S vector is precessing around J. That's why mu Ls will also precess around mu J, and that's why it will have two components along J. One will be along J vector and another or J or minus J vector, and another will be the perpendicular to J vector. The sum of that perpendicular component will be 0 due to one complete revolution. So it will have effectively one component. Now we can write mu J in terms of mu Ls dot J cap into J cap. So its effective component will be mu Ls dot J cap along J cap. We can write this in terms of mu Ls dot J vector by J square into J vector. Now as we know that mu Ls is equals to minus E by 2m into J plus S by J square. So we'll put that value of mu Ls in this expression. Now we'll get mu J is equals to minus E by 2m into J plus S by J square dot J vector along J vector. Now we can write it in this term in this way, that it is equals to minus E by 2m into G into J vector. This G is the lande factor, where G is equals to J plus S by J square dot J vector. Now J equals to J plus S by J square into J vector, which is equals to J square plus J dot S by J square. Now as we know that L equals to J minus S, that means L square is equals to J square plus S square minus 2J dot S, or J dot S equals to L J square plus S square minus L square by 2. Since G vector is equals to J square plus J dot S by J square, now we need to put this value of J dot S in this expression. So if we put the value of J dot S in this expression, we will get the value of G, which is equals to J square plus J square plus S square minus L square by 2 by J square. Or we can simplify this term in this way, that G equals to 1 plus J square plus S square minus L square by 2 J square. Now g equals to 1 plus j square plus a square minus l square by 2j square. Now replacing this j square, a square and l square by their quantum mechanical values, we'll get the expression of g in this way, that g equals to 1 plus j into j plus 1 plus s into s plus 1 minus l into l plus 1 by 2j into j plus 1. This quantity g is called the lande factor, and its value will depend on the values of j, l and s, and it is different for different j, l and s values. Now the total magnetic moment of the electron can be written in this way, that mu j equals to minus e by 2m g into j vector, which is equals to minus e by 2m. Now we will put the value of g in this expression as g and root over j into j plus 1, which is equals to minus mu b g root over j into j plus 1. Now we will consider one example. Calculate the lande factor and the total magnetic moment for the state 2s half. For the state 2s half, the value of L, that is, it is A, so value of L is 0 and J is half, and S equals to half, because 2s plus 1 is 2, that means S equals to half. So now we need to put the values of L, J and S in the expression of G, that is G equals to 1 plus j into j plus 1 plus s into s plus 1 minus l into l plus 1 by 2j into j plus 1. Now we need to put the values of l, j and s in this expression. If we put their values, the value of g will be 1 plus 3 by 4 plus 3 by 4 minus 0 by 2 into 3 by 4, which is equals to 1 plus 1, that is 2. Now for this state 2s half, we have calculated the value of g, which is equals to 2. Now the total magnetic moment mu j equals to g root over j into j plus 1 mu b. Now we need to put the value of j, which is half, in this expression, and as we know from our previous calculation that g, the value of g is 2, so we have put we need to put the values of j and g in this expression, and we will get the value of mu j, which is equals to 2 root over 1 by 2 into 1 by 2 plus 1 mu b, which is equals to root over 3 mu b. So I think now you have a clear idea about lande factor and how to calculate lande factor for a given state, and on our next class we will discuss about Zeeman effect. Thank you everyone.